All right, hi, my name is Hamzah Ahmadi, and my project for this summer was computer vision for dietary assessment. All right, so how many people do you guys know say they're going on a diet each year and then fail within like a week? That's a lot, right? So there's 45 million Americans who try to go on a diet each year, and there's $33 billion spent on weight loss products each year, and only about 20% of those people actually make it long term, which is like over a year. So maintaining a diet is hard, obviously. So my research question was, how can we do lightweight dietary assessment? And the current most popular method for keeping up with your diet is manual logging. And there's a couple main problems with that. Number one is people tend to guess their portions and their macronutrients, and that leads to incorrect results. So as you see here, uh, a lot of these manual logging apps have options for dishes that range a lot in portion size and calories, and people just pick like the healthiest one they see, and again, that leads to incorrect results. And then the other problem with manual logging is it encourages inconsistent logging. When you have your food in front of you, you don't want to take out your phone and then type every single thing that's on the dish, all the calories and things like that. So we propose automatic food logging. And basically what that is all you do is you take a picture of your food and it gives you all the information right away. It detects everything automatically. So here I just have an example of what the screen will look like for the user interface. You have a picture of the picture that they took, and then it'll just have a quick breakdown, and then these can be your logs, and then you'll have a week summary too. So you can see basically your average of weekly food intake in comparison to just one food intake, and that'll have you basically getting a better idea of what you've been eating on the average. So next we have the methods. So we are using basically machine learning in order to do the automatic food detection. So with machine learning, we have to train our models, and we're using 3 different data sets to train those models. We're using FoodSeg 103, Google 5K, and each of those have their own feature. So one of them was strictly for segmentation, one of them was strictly for basically ingredient classification, and then we had another data set which was AICrowd Food Recognition, and that had both of them. So here I just have an example of what these data sets look like. We have a realistic image of what somebody would take of their food, and then you have the basically what would show after the image goes through the machine learning process, the segmentation, and the ingredient classification. So what we use for our machine learning, we used MobileNet because it's easy to train, it's lightweight, and it's able to be easily implemented within a food app. And then for segmentation, we made it a lot easier for ourselves by using segmentation, which is basically something like a Python library, and it just makes the segmentation process a lot easier. And then these 2 tables right here, I just have a breakdown of how many images were in each data set and for each category. And then for the results, we pretty much just had this top row was only for food ingredient classification. So that's why there's no accuracy reading for the segmentation categories. So that was for the food ingredient classification. And then the second model that we use was strictly for segmentation. And that's why there's no accuracy readings for the food ingredient classification. And the third one was both at the same time. So that was a multitask model. And that actually turned out to have the best results. And the second table I have here is just a reading of each different food group. And that's important because our data set had kind of an imbalance in food groups, and that was reflected within the data sets. And I'll talk about that more in a second. And then for the results here, we have, this is something more for the user interface. After the images go through the models, it comes out with a segmentation mask, and basically that's just a dark image, and it has different pixel values within the image. And then I extracted those pixel values as you see on the left, and each pixel value just corresponded with the food group. So for example, 0 was for meat, 1 was for dairy, things like that. So we just turned that list into a pie chart, and this is how we display the information back to the user. So the implications that we had was just that the combined multitask network was the most accurate for reading food analysis and displaying it back to the user. And for our future work, we want to use a lot higher number of images for training. We use a very low number, I think, in the tens of thousands, and ideally we want to use billions. And then that table I showed earlier, and I'll go back to it, this bottom one, basically as humans, we tend to eat certain food groups more than others, and that was reflected within the data. And, it would show meat more than nuts and seeds and images. and the model turned out to learn meat more than other food groups and things like that. So there was an imbalance of how accurate the readings were for each food group. So if we have a more balanced number of data for each food group to start with, we can have a more accurate reading for each food group to end with. And then we want to add more layers to the model. Like I said, we use MobileNet, and that's a very lightweight, efficient method. But if we're able to customize it a lot more, we'll have a more accurate reading. And the way we customize it is by adding network layers to it that detects color, depth, things like that. And I want to thank my mentors, Christina Chung, David Crandall, and Wesley Koo. And I want to thank my partner, Brandon Liu, and our funding resource, the NSF. If you guys have any questions, feel free to email me. This is my email right here. Thank you so much.